Okay, thanks a lot, Shane, for the nice invitation to your institute. It's an honor to be here at the Institute for Advanced Studies, especially with such a nice timing because we're actually like 3 days away from the exact date that Schroedinger submitted his paper on wave mechanics 100 years ago. And since he worked here at this very institute as first director of the school until his retirement, I wanted to use this occasion to talk a little bit about the Schrödinger equation and then its generalization to open systems, Lindblad equation. Because actually, last year we celebrated the centenary of matrix mechanics. This year we could celebrate centenary of wave mechanics, but we can also celebrate half a century of the Lindblad equation. So we have a double anniversary, and I would like to celebrate it. Talk a little bit about the algebraic structure underlying those dynamics, and give some old and new insights on the way. So, okay, what is the mathematical setting for this? So there are basically two main themes for this talk. One, which is about the kinematics, which I call star algebras, and the dynamics I call master equations. Because, I mean, there are lots of star algebras. So, Banach algebras with an involution. But then you have an additional condition, the C-star condition, which is a relation between this involution and the norm of the algebra.
What do you mean by the phrase star algebra?
Well, it's like the best of the star algebras, right? This is just a joke. And the master of master equations, because it's like the most prevalent in physics. Because you have this additional C-star condition, which is needed in lots of physical settings. And then the master of master equations, of course, you have lots of master equations generated by Liouvillians. But then you have, in the quantum setting, the CPTP, the completely positive trace preserving semicubes, and they are generated by Lindblad, and I will talk about this. And in both themes, I will have two cases. So for the star algebras, we have the commutative case, which is the classical case, which was characterized by Gelfand, which is just basically continuous functions on a compact Hausdorff space. And then the non-commutative generalization, the more general case, the quantum case, which is bounded operators on a Hilbert space, which is then given by the GNS, the Gelfand-Neumark-Seeger construction. And the same, but in analogous separation in two cases you can have for Lindbladian. For the finite settings, you have the Gorini, Kozakowski, Sudarshan characterization. And for the infinite setting, you have the Lindblad characterization of those semigroup generators. And in this talk, I will go from left to right. So we start very, very easy with the classical case. And then we end up with the most general quantum case. So if you look in the classical physics, you look at the Poisson algebra, you have phase space. So if you have a physical system given with a configuration manifold M, and then you construct the cotangent bundle over it. So you have those cotangent spaces which are fibers in this fiber bundle. And then locally it looks like R2. And then the phase space is equipped with a natural symplectic structure. And there's more general things like Kähler manifolds and so on, but just focus on the simplest case. You have locally R2, and you have the symplectic structure that gives you basically Hamiltonian dynamics. So this is given by the symplectic matrix J, and you can write then the time evolution of any point in your phase space in this way. And then related to this is the Poisson bracket, which is just basically the directional derivative of the function along the Hamiltonian flow that is generated by another function, G. So then you have this Poisson bracket. So I just write this all now in 1D, right? You can always sum over all degrees of freedom if you have higher dimensions. And then you look at the structure preserving maps. in this symplectic space. And those are called symplectomorphisms, or in physics, canonical transformations, that preserve the symplecticity. So it leaves the symplectic matrix J invariant, and also, applying the symplectomorphism on those functions, and then taking the Poisson bracket is the same as taking the Poisson bracket and then applying acting such a symplectomorphism. And now the important thing to note here in relation to star algebras is that we actually have a hybrid algebra. So normally, like in school, you learn, okay, an algebra is a linear space with an operation, but here you have linear space, function space, and C of x, but then you have two operations. And you have a symmetric and an antisymmetric one, associated and non-associated, commutative and anti-commutative, which is exactly this product of functions, which you take pointwise, and then the Poisson bracket. And then this one operation, the Poisson bracket, gives you an algebra that is non-associative, and the associativity with respect to the Poisson bracket is replaced by this Jacobi identity, which is just true for Lie algebras. And the compatibility between those two operations, Poisson bracket and the pointwise product, pointwise multiplication of functions, is ensured via the Leibniz law. So you get the compatibility of two operations, and you have a hybrid algebra. But now, if you look at it from a different point of view, and you say, I want to dehybridize, I want to have a normal algebra where I have a linear space in one operation. Then you can say, okay, I introduce multiplication and Poissonication operators that just are left or right, multiplication, or left or right acting with a Poisson bracket. So you can define those operators, right, on this function space. And now you have normal algebra, where you take as the element of this algebra those operators, mg and pg, multiplication and Poissonication. And then the composition is
the space X always compact, or can it be non-compact?
Normally it's compact because you need a compact Hausdorff space.
Do you ever deal with non-compact X?
I don't think that this works when it's non-compact.
You don't do it.
No, we were looking at compact Hausdorff spaces, C of x.
What do you get out of this?
Yeah, I will come to it. So the point is, you dehybride this operator algebra. You have not this hybrid structure anymore. It's not algebra. You have one algebra where you have a linear space of those operators, and the composition is now the new algebra operation. But then you see it's a non-commutative algebra. And this basically shows you have non-commutative properties already in the classical phase space, right? If you look at this from this perspective. And so if you really want when you want the star algebra in the classical setting, where it's commutative, you have to leave out this Lie algebra, the Lie bracket.
But the cotangent bundle being compact is going to be rather restrictive.
Well, you need this for this star algebra construction later on. Because the Gelfand, I will come to it right here, next slide. So the Gelfand construction says, if you have a commutative C star algebra, calligraphic A, then there's always an isomorphism. You can always identify this commutative abstract algebra with continuous functions on a compact Hausdorff space. And then you introduce the so-called Gelfand spectrum, which are just algebra homomorphisms from the algebra to the complex numbers. So these are just functionals. You evaluate them on the algebra, and then you have the Gelfand transform, which maps each element of your abstract algebra A to the so-called Gelfand transform A hat of this, which gives you a function, continuous function on this Gelfand spectrum. And the definition of this Gelfand transform is just that this function A of phi, where phi is this, or phi is this algebra homomorphism, is just phi of A. It's just a very natural pairing. And if you have a non-commutative algebra, this doesn't work, of course, because then you cannot, then not all those functionals will give you homomorphisms to the complex numbers, because the complex numbers are commutative. And then you need another construction, which we'll get to next, on the next slide, the genus construction. But you can also look at the star algebra C of x from another point of view and say, well, we have this space of functions C of x, but we can actually look at the Hilbert space, not just the Banach space C of x, but introduce a measure, an integration measure mu. We look at this Hilbert space of square-integrated functions on x, and we introduce the inner product, just as is known, equation over this measure f star g, and then you now have again an operator algebra of multiplication operators. You can just take functions, and they're just acting on other functions via left or right multiplication, and those left or right multiplication operators are now the elements of your algebra, and they act on functions. And now, shortly after Schroedinger introduced his wave mechanics, Koopman realized you can actually get the whole classical physics setting into the Hilbert space picture as well. If you look at densities on your phase space, rho, probability distributions, and you now say, I introduce a Koopman wave function where the modulus square is exactly this density. So you get those densities on phase space, and the square root of it is your Koopman wave function. So you basically get the wave mechanics for thermodynamics, or let's better say StatMech, where you have distributions over phase space, and you can still, in the classical setting, put this in this Hilbert space picture, because you're embedding this multiplication operator algebra into B of H as a commutative subalgebra. And this brings us now to the star algebra B of H, where now the Gelfand construction has to be generalized to the Gelfand-Neumann-Siegel construction. You first need a notion of positivity, then you look at the dual space of the algebra. This gives you all the linear functionals. Then you need a state space. Those are all special linear functions that are positive. For positive operators, they are very positive. And unital, because you need normalization for probabilities and so on. And then now how you get your representation of bounded operators in the Hilbert space from this abstract algebra telegraphy A is that as a representation space, you first have to pick a state. So you have those linear functions, states on your algebra. Now you have to pick a state. Now the representation will be state dependent. And if you do this, then you can introduce this map, which for now is semi-definite, because all those linear functions are greater or equal to 0. So now you have to mod out this indefiniteness. Like you have to mod out the null space in this Gaussian space. You take the algebra, mod out the null space, and then you get a pre-Hilbert space. And because of this Gaussian space, you now have the equivalence class C. And now you can define an inner product, which are positive definite, which you need. Right? So now you have a true inner product, and this gives you now, if you do the Cauchy completion with respect to the norm induced by this inner product, you get a Hilbert space. And this gives you the Gelfand-Neumann-Siegel representation, where now it says you can give me any general C-star algebra. It doesn't have to be commutative, it can be non-commutative. And if you pick a state, you always get a generous representation I, where this algebra can be represented by bounded operators on a GNS Hilbert space, and this Hilbert space will be state dependent. And this works again by multiplication operators. As before, as in the Gelfand constructions of commutative algebras, you just act now with left or right multiplication on those equivalence classes, and you always get your state back. So the state you chose for your representation, you get it back via this way. It's just the inner product of the identity, the equivalence class of the identity, and then the algebra element. So now we come, so this is the kinematics, but now we need to talk about dynamics here. How do you get time evolution? So we take a step back and say, from a general point of view, for any dynamic system, you always have evolution of states and observables, and this can be very general. So it's just given locally x dot via a field, a vector field. So this gives you your time evolution of the state. And if you integrate it, you get the flow in phase space, right? Or it doesn't have to be phase space. It can be any abstract state space in whatever dynamic system you consider. And the observables now are functions of this. And their evolution is given by the Liouvillian. So this takes continuous functions on your state space of the dynamic systems again to continuous functions. And if you integrate it, it gives you also an operator, which we will call the Copenhagen. And those two are now very important for our further discussions. And the point is that algebraically, what they are is the Liouvillian is a differentiation operator. So it's basically just the inner product of V nabla and the composition operator for the Copenhagen, because what the Copenhagen does is it takes the function at some point, at some starting point, and now you want to know how the function is evolved at a later time. You look at the observables, not the states anymore. For states, you know what the flow is doing, but now you're not looking at the flow of your state space, you're looking at the functions, and you want to see what happens to the functions when you flow. You go along the flow.
I don't understand what you're doing there. I mean, you've got f of t is equal to k of t at f of 0.
Yes. Just like here, x of t is equal to this symplectomorphism, the flow, that takes 0 to xt.
Okay, but let's go down to the other answer.
Yes.
What is k meant to be doing there?
So this is acting on your function at your starting point.
I can see that, but where did it come from? It's just a function from c of x to c of x.
Yes, just like here, you integrate the vector field and you get the flow. Here you integrate the Liouvillian and you get the Copenhagen.
So what do you get from this? This is formalism.
Yeah, we will get to it. This is like all the framework in the background. So the point is here, the dynamics linearization that you achieve, because that's sometimes that people don't appreciate. You have nonlinear dynamics on the state space X, but now if you don't look at the states, but you look at the observables for any dynamic system, you get linear dynamics, right? Not only in quantum theory. In the quantum theory, of course, you already have linearity at the state level, but now you have linearity at the observable level. And so this is, this was, Koopman did this in 31, like shortly after wave mechanics by Schroedinger. He realized, we can formulate nonlinear dynamics in a linear setting. And this led to this Koopman von Neumann quantum or Hilbert space formalism for classical physics. And then later on, many decades later, the machine learning community.
I think what you're saying here is that your flow is a first order differential equation.
Yeah, so this is of course
in the latter part, that's really all you're saying at the end, isn't it?
No, the important thing is here that this is a deterministic vector field. If you have stochastic terms there, then of course the whole thing doesn't work.
But they won't obey Leibniz.
So
the fact that it obeys Leibniz.
I look here at this. I look exactly at this. So here I say it's valid for deterministic flow, but it's violated for stochastic flows.
Yeah, of course.
So
anything that doesn't obey Leibniz, if it was the
yes, if it's not a derivative, exactly. So we're looking at this algebraic structure, which is valid for all deterministic flows. But as soon as you introduce stochastic terms,
when it's more restrictive than deterministic, it has to be first order. If you put a second order term in there, it would still be deterministic, but it wouldn't satisfy that.
We will use this setting, right? It's Markovian, course. So you always know if you have the state at one time, it tells you what happens for the state at the next time state. So it's a Markovian picture. It's not non-Markovian, right? It always takes you from one step, from one state to the next. And then this is also valid for the Poisson bracket, this automorphism and derivation structure, in case of Hamiltonian flows. So of course, Hamiltonian flows are deterministic, so it's a special clause.
It still needs to be restricted. You won't have it if it's got a memory of lumber.
Okay, yeah, I mean, there are so many words floating around in literature. Like, if you have a vector field E and there are no stochastic terms, then this holds. And so you have this, and then of course there's a subclass of deterministic flows, which are Hamiltonian flows, given by the symplectic structure. And then you also have an automorphism derivation on this Poisson algebra.
I have another question. Sorry to be interrupted, but
Yes.
if Koopman was working in 1931,
Yes.
He could be viewed as post-Schroedinger.
Yes.
Something a bit extra. Do you ever get to relativistic? I mean, do you ever get to a relativistic system?
Oh, we're not talking about relativity.
But that's a big failure.
No, but I'm talking about Schrödinger and Lindblad equations in a non-relativistic setting. We're not talking about theoretic.
Does this formalism ever go any further?
Yes, but I mean, I have to go on to get to the point. So, so the point now is that the Kopenhagen and the Liouvillian, they're both linear operators, as we saw, but the Kopenhagen is a bounded operator, where in general the Liouvillian is not. There can be unbounded generators. And so you need this whole functional analysis semi-proof theory, right? Where you say, if you have strong connectivity, or the Liouvillian theorem says it's an if, only if condition on the domain has to be dense, and there are some bounds and some conditions on the resolvent of the Liouvillian, then you always, with this Liouvillian, you generate a strongly continuous semi. This is the Liouvillian.
What do you say was not bound?
The Liouvillian is in general not bounded. Can be unbounded. They are unbounded Lindbladians. Lindblad did it for bounded, but I mean, the generator could be unbounded. So again, if you go to the Koopman von Neumann picture, if we have a divergence-free system, then we can look at this Liouvillian, and this gives us now basically a Schrödinger equation in this commutative setting, where you have now the Koopman wave function that is now, the time evolution is now generated by the adjoint of this Liouvillian. And if you have, for instance, now again a Hamiltonian setting, so in this case, your vector field would be given by the gradient of the Hamiltonian, I mean, in coordinate dependent notation, right? And the symplectic matrix, then you can write it like this, and then again, you have, as your Liouvillian, you have pH, the personification by the Hamiltonian, and the Koopmanian would just be this, right? Nested Poisson brackets. If you have a if you have not a divergence-free system, then there is a generalization to this also in this Koopman von Neumann picture, where you still get unitary groups on this Hilbert space of strange Hilbert functions. And now, again, you have this in the classical setting, but of course, this is all just, there's everything commutes, right? So you have no interference effects, nothing non-classical happens, just the mathematical formalism, as we pointed out. And if you now go to quantum systems, now you have you don't have to worry about linearization via Koopmanians and so on, because you already have linearity on the state level, right? You have linearity everywhere. So you have the linear operators on a Hilbert space, and then you can look at the ideas, the Schatten classes, which are just given by all those linear operators that are finite in this Schatten norm, and then you can look at those various ideas. Those are left and right-sided ideas. So meaning if you multiply any element of those ideas with any other operator of the whole algebra, you always will end back in this ideal. Right? It's like a black hole by left or right multiplication. And so here you have finite rank, you have trace class, you have Hilbert-Schmidt, you have compact, you have bounded, and you have linear operators. So everything is linear. And you have the Schrödinger equation, you have the Schrödinger picture, or the Neumann equation, you have the Heisenberg picture for the observables. And again, we can look at the algebraic structure for them. And again, we see automorphisms and derivations for closed systems. In open systems, this will not hold true anymore. Then the Lindblad is not a derivation of the operator algebra anymore. And again, the generated unitaries are bounded. That's the whole point of the Stone-Neumann theory and the representation, the uniqueness of representations. But the generators are in general not bounded. And this is basically the Stone theory. And so now, if you look at open systems, then we wonder what happens to the evolution on a subsystem. And then a natural thing to consider is to say, well, okay, you know, if I just have an observable f of t on a subsystem, the obvious thing would probably be to embed it in a larger system, the whole system. Then we know what evolution works, how evolution works. It's just unitary action on the whole system. And then we project it down to our subsystem. And then we look at it and see what happened to our subsystem observable f of t. That's exactly what we do here, right? So f tensored by the identity is just a trivial operator on the rest. And we dilate to a higher space, and then we project down again. And so this is like, from physical intuition, it's quite natural to think this way. But the important thing is that this is exactly what was characterized as a so-called completely positive map. Because already in 55, Steinbrenner characterized all completely positive maps, so meaning that if you have some map phi that goes from one star algebra A to another one B, and normal positivity would just imply that any operator that is positive gets mapped to another positive operator, but not completely positive. Complete positivity is something much stronger, because now you kind of look at all the tensorial extensions, because you could ask, well, okay, I have my subsystem and I let it evolve, and it's of course important that on the subsystem states stay positive. But it was realized that there are maps that could be positive on the subsystem, but not stays positive on the whole system. And this cannot be. You know, even on the whole system, if you look at the whole system, positivity has to preserve quantum physics. So then you introduce those tensorial extensions here, where you act trivially on the environment, on the extension, and let your subsystem evolve by phi. And then you look at those matrix algebras with entries in the star algebras A and B. And then you say, well, it's completely positive if for all tensorial extensions for any n, this thing is positive. And then what Steinbrenner achieved was this characterization that complete positivity, this function class, is exactly this. Can always be written like this, where you have, you know, the action on some operator of the star algebra, and then you just, you know, take such a bounded operator, you go to a different Hilbert space, you act with a representation pi, so this is a star representation, it respects all the properties of the star algebra, you know, the norm, and so on. And then you project down again. And that's exactly what the physicists want, right? This is exactly what we want for evolution in subsystems. And so this is very important that this was realized, but this is exactly the notion of complete positivity. And then there is a special case for that, but this only works in finite dimensions. This works in any dimension. In finite dimensions, if you take as the star algebras, now.
So what is the condition on V? Is V times V star the identity or a projector?
Oh, you mean this?
Yes.
That's just an arbitrary dilation. You can just embed it in a larger Hilbert space and then project it down again. This is just like what is always done when you do the Stein transformation.
I expect that it's something like partial isometry.
Yeah, it's in partial isometry. Exactly. It's not a unitary, but it's a partial isometry. It's a little bit more general than in the unitary.
Yeah, no.
You're right. I mean, I cannot, I apologize if I cannot, really write down all the details because it's a lot of stuff. But the Schroedinger characterization is for finite dimensional settings, and then you get this Clauser transformation. If you have finite dimensional Hilbert spaces. And so, why should we care about this complete positivity? This is all a lot of abstract things, but I would claim, my argument is that complete positivity and the distinction to just positivity, so P unequals Cp in quantum theory is almost as important as P unequal Np in computational complexity theory, where you have complexity classes P, and then you have the polynomial complexity class and the non-deterministic polynomial Np. And this distinction is very important in computer science, right? But it's so far it's a conjecture, it's not proven yet. Whereas, but everyone assumes it. Like almost all things or proofs, they are based on this. The whole thing, like most fields in computer science would collapse if this is not true. But here we know it's true. It's proven. It's a consequence of the action. And so there's a nice history that although the notion of complete positivity was already characterized by Steinspring in 1955, physicists didn't take notice. It was completely unknown. And so people tried to find general dynamical laws, like how does quantum states evolve, but they didn't know about this complete positivity that I introduced in the previous slide. And so they looked just at positivity. And as I said, this is not enough because, there are maps that are positive on the subsystem, but not positive on the whole system. But people didn't know, so they did all kinds of stuff, already in 61 by Sudarshan, 69, and so on. But they all had mistakes in them. So they found the right equation for the generator. It's the same equation that we use today for Lindblad equations, but with the wrong assumptions. They confused positivity with block positivity and so on. So it's very interesting, the whole history. And I mean, I will not go into all the details here, but you can find out that if you have any family of hermiticity preserving superoperators, so this is always what you want, of course, in physics, self-adjoint operators, which give you the observables, they should stay self-adjoint, so the dynamics should not destroy hermiticity. So the least you would want is hermiticity preservation between those those algebras of bounded operators. And if you then look at the generators, they always have to take this form, just because of hermiticity preservation and trace erasure. You want then trace preservation for the dynamics, and so you need trace erasure for the generator. But now for quantum dynamics, we know that hermiticity preservation is not enough. You need a stronger thing, which is called complete positivity. But here the problem is that for hermiticity preservation, this is true for the derivative and for the inverse. But it's not the inverse of a completely positive map is not necessarily completely positive. I mean, you can take the inverse if you just look at the superoperator. You can just most of the time take the inverse, but then you realize it's not completely positive. And so what then people did, they started with finite dimensions, so not in the general setting, and they just looked at time local generators, and they found that it's always given by this in this form, where you have a traceless orthonormal basis consisting of those Fs. And for a Hilbert space dimension of capital N, you have n squared minus 1 of those, and then the last basis element is just the identity. And then you can always write this generator of this time evolution like this, where you have some correlation matrix here that correlates all your dissipation channels KL and is time dependent. And this general structure is actually correct for any open dynamics hermeticity preserving, trace preserving maps. And if you then restrict this correlation matrix to a positive matrix, so all those have to be positive, then you identify all the completely positive maps that are divisible, meaning that you can decompose your map at any point into two factors, right? That you can divide it. And it goes a little bit to the point we had earlier, like, this is of course also related to Markoviani, and like people sometimes forget about this, even in very basic settings. Like even I was very surprised by this in the double slit experiment. When you show that there's a contradiction to the classical interference pattern, right? You expect. You only get this contradiction when you assume Markovianity, when you assume that you can divide the whole thing into two steps, so that you go to the slit and then from the slit to the screen, and so you have a probability distribution from the source to the screen times probability distribution from the screen to the from the slit to the screen. So this divisibility is a very sneaky thing that sometimes gets overlooked.
Can you repeat that statement about the double slit? I didn't quite catch it.
Yeah, when you have the famous double slit Gedanken experiment, then when you say, oh, we get an interference pattern that is different from the classical expectation, you always assume that you can factorize the probability distribution, that you get that you get the probability distribution for getting some signal at some point on the screen, that you can factorize it into two steps, from the source to the slits, and then from the slits to the screen. And that's a divisibility assumption. And so this is a little bit related to this, that there are maps, that could not be divided into smaller steps. Oh, and very important, if this divisibility fails, then the condition on such a general Liouvillian that solves this, that is the CP solution to this, is simply unknown to this very day. So there's a lot of things, but if the CP divisibility holds, then you still have the time dependence, right, of this correlation matrix connecting those dissipation channels. And there still you don't know the general form of those entries. Like if you have dynamics, it's still not known how to get those entries of this correlation matrix. It's an open problem for open systems.
So just to refine it in a matrix setting, the complete positivity for matrices is that every submatrix is also positive. So it's essentially the same idea.
I didn't, but here it just means that that all those entries are positive.
Yes, it did.
Yes, here. I mean, there are different notions of positivity. One notion of positivity is that the eigenvalues are positive, or
that the eigenvalues of every submatrix is positive.
Yeah. So here, here what I mean is those entries, the matrix elements are all positive. And then you still have this time dependence. And for this time dependence, for the general case, you don't know what to do. And then one thing you can do to get out of this conundrum is, of course, to sacrifice this time locality, right? And say, now I look at non-Jacobian master equations, and now my time evolution of my density operator is, characterized by a memory kernel that accounts for all the things that happens along the way. And there can be, memory stored in the environment that comes later back. And this is then encapsulated in this memory kernel. This is one thing, but this is very, this is very important. You don't know all the details of your dynamics. The point in physics most of the time is to get some reduction in complexity. So then what's the alternative? The alternative is to enforce a semicon structure, right? So say I postulate a semicon structure for my time evolution. So this is basically, this has several things. There's time symmetry, time translation symmetry here in this equation, but foremost, most importantly, the Markovianity. So you have no memory, There's no information backflow from the environment. And now you look at those semigroups, and now you try to find out, well, if I don't have this, maybe I can do something with those so-called quantum dynamic semigroups. And that's what people did, starting basically with Khodorkovsky. And the problem was, and now we come back to this importance of the distinction between positivity and complete positivity, is that Khodorkovsky, he just looked at positive semigroups. And he didn't get quite far. Like he found some properties, but it's still, and to this very day, it's still unclear. Like if you just assume positive maps and you have a semigroup of them, what this implies for the generator, and in particular for this correlation that you see in the generator. And so this is what I pointed out in the earlier slide. It's like it's very important to see that you need complete positivity for the semigroup. And then once the news spread about this in the 70s, that you need this complete positivity that was characterized earlier by mathematicians, then Khodorkovsky and his collaborators Liouvillians and Darshan, they found actually the correct generator that looks very similar, but now you have no time dependence here. Right? And the Fs are just like in the general case I showed before, where you have just the trace list of a normal basis. This is the effect of the Hamiltonian. There can be a lamp shift into the renormalization effects of the environment. But this is now a very nice characterization. And they showed that positivity of this matrix is in one-to-one correspondence with complete positivity of the semigroup. So one implies the other. The interesting thing is that the connection between positivity of the semigroup and the form of this Khodorkovsky matrix C is not known. So somehow, it looks like positivity should be the easier thing. It should be mathematically easier. But actually, it's harder to characterize. And the nice thing is, we can be very grateful that actually for physics, the easier structure is necessary. Because we need complete positivity semigroups. And then Lindblad did the same, but he looked now not at just finite matrix algebra, as we showed along the last slides. He looked now at the whole C-star algebra bounding operators in the Hilbert space, and he found this, which is basically the diagonal form of this. You could diagonalize this Khodorkovsky matrix C, and if you diagonalize it, then you get the eigenvalues on the diagonal, right? And so you have the spectrum, and you can incorporate those values in those operators. You just redefine those Fs, make them two Ls, and then you get the diagonal form of a dissipator, and that's the standard form that you use. That is now called the Lindblad form. And here again, you have a one-to-one correspondence between complete positivity of the semigroup and complete positivity of this map that appears here, where you basically can then use a Krauss decomposition of this completely positive map phi to get those operators as. So those Lindblad jumps that are like they are normally called in the literature, those jumps are actually the Krauss operators then of this completely positive map phi, which characterizes now our completely positive semigroup. So again, there's a bijection. There's a one-to-one correspondence between complete positivity of semigroup and complete positivity of this. And again, for the positivity only, it's much more contrived because there's only one implication. It's sufficient. The positivity of this map is sufficient for the positivity of the semigroup, but it's not necessary. Whereas for the complete positivity, you get sufficient and necessary partitions. And so the point is that both arrived at the same picture for this open system dynamics, but one group, the GKS, worked in the Schrödinger picture, whereas Lindblad worked in the Heisenberg picture, here in the finite dimensional setting, here in the infinite setting. So they started with those two pictures, but they arrived at the same conclusion. And this is why it's important to sometimes abstract away from the Hilbert space picture and look really at the algebraic structure. Why do I claim this? I mean, I have to justify it, right? I have to kind of sell this. Why is this star-algebraic perspective so important in my view? Well, there are several reasons. I just picked some. If you look, for instance, just at the Schroedinger equation, you can rewrite this, and then you could define this gauge covariant derivative. And this is basically just like a non-Liouvillian gauge theory, where now you have a fiber bundle where the Hilbert spaces are fibers on the points t, which parameterize your time, which is the base space of the fiber bundle. And then the time evolutions in this fiber bundle pictures, they are just sectional of this fiber bundle, right? This is sometimes used in curvature of this. And most importantly, those trajectories, the different time evolutions, they can be mapped into each other via those gauge transformations. So you have unitaries Vt, they transform your observables into those transformed observables. They transform the unitaries, the time evolution, into this, and the Hamiltonian gets transformed into this. But the whole thing, the whole Schrödinger equation stays the same. So this kind of, gives some doubt on the ontological status on the Hilbert space, because like you can transform it, and you can even transform trajectories into each other, and you can rotate each fiber into each other locally, and the whole dynamic stays the same. The Schrödinger equation has this invariance still there. And this is also, like from the perspective of Gell, van Neumark, and Siegel, where you have a C-star algebra, non-commutative C-star algebra, you can then always construct a Hilbert space from it. You just have to pick a state, as I showed you in the construction. So it will be a state-dependent representation. But you can always embed any non-commutative C-star algebra, any abstract algebras we could write down. You can embed them as a sub-algebra of B of H. And you always get a Hilbert space out of it. So this is why it's a contrast to the standard approach. In the standard approach, you have first the Hilbert space, and then you kind of have you have an algebra of operators acting on it. The self-adjoint part gives you the observables, the trace class positive one gives you the density operators for the states, and so on, or at least for the normal states. And the algebraic approach kind of turns it on its head. It inverts the logic. It says we start first with the abstract algebra, and then we get Hilbert spaces out of it. And many of them, because you could pick any state, and the representation space is state dependent. So you get lots of Hilbert spaces. So this is another argument why you should maybe not give such a central status to the Hilbert space and what happens in the space, but more on the level of the algebras. And also, one should say that already at the very beginning, when we had the Stone von Neumann theory about uniqueness of representations, when you have the normal commutational relations, and now because there's general problem with unboundedness again, you have then to exponentiate them via spectral theory. You can do this you get bounded operators, unitaries U and F, U and V, those are now bounded. And then you can restate this commutational relation into the wide gradient relation. It's basically just the same, just now for bounded operators, which is this. And then Stone von Neumann in that theorem could show that all operators that fulfill those relations, they are always unitarily equivalent to the Schrödinger representation, right? But this is only true for finite degrees of freedom. If you go to infinite degrees of freedom, this is not the case. Then you get lots of non-equivalent unitary that are not unitarily equivalent, lots of representations. So again, then you should maybe put not so much importance on the Hilbert space representation, but really just the operators and their relations, because that's what important, the algebraic structure. And so there are many other reasons, like non-commutative geometry with the Gelfand triple, Alan Kohn did, or in quantum proofs, or non-locality, in many body physics, you sometimes have non-local states, and for all this, it's better to work in the star-algebraic picture. So this is a justification, and now we'll get some results. Oh, this is very bad to see. So I will zoom in. So now using this algebraic approach, we can talk about some properties of our Lindbladians. I mean, symmetries, for instance. Also, we can talk about the asymptotic behavior. And one thing that is of interest is non-equilibrium steady states. So normally in Lindbladian systems, they describe systems where you have couplings to several thermodynamic reservoirs, so they are non-equilibrium systems. And then you could look at the fixed points of this. So those are in the kernel of the Lindbladian. And then the question for a long time was, how can we identify Lindbladians that have unique fixed points and ones that have multiple, that could settle to a multitude of states? And there were in the past in the literature, mainly in the 70s, there were some conditions, starting with Spohn, who found this criterion here. It's a sufficient condition. Here again, you have this Kosakowski matrix C that I talked about earlier, and you look at the kernel and its dimension. And if it's smaller than half of the Hilbert space dimension, then you have a sufficient condition for the uniqueness of the fixed point. And you know for sure that your Lindblad evolution will always end up with the same state at the very end. And there were other conditions here also. Again, you look really at the operators and the algebraic structure. You look at the commutants. So that means just you take all the operators that commute.
So the previous one was for finite matrix system, was it?
Yes, because you have the Kosakowski matrix.
Yes, yeah, you're just a finite dimensional vector space.
Yes, space. Yeah, exactly. So then you have relation between the kernel of the matrix, its dimension of the kernel, and the half of the Hilbert space dimension. Here you have a different one, which is actually necessary for sufficient condition. So right here,
so is there any intuitive reason as to why it's 1/2?
Why it's 1/2? No, because I mean there are lots of equations. There's not really.
Is that sharp? Is that sharp?
No, it's less or equal.
Less than or equal.
Mm-hmm. Less or equal. So, but the second criterion I show here, that only applies if you have a positive definite state, which is also called phase state. So, because the state could be greater equal 0, right? So the problem is always this as was the case earlier for inner products. If it's non-definite, if it's semi-definite. And so this was pointed out by Spohn then. And then if you look at W star algebras as opposed to C star algebras, so you take a different topology, but they are characterized by the fact that they are owned by commutants. So you take the commutant, all the operators that commute with the operators, and then you take the commutant again. So all the operators that commute with the operators that commute in. And if that is equal the original algebra, then you have a W star algebra, also called von Neumann algebra. And so you can then restate this and say, well, if you have a positive definite state, then it is unique. The system has a unique non-equilibrium steady state if this set here generates the full operator algebra. But now there has been progress on this, because now we even have a criterion that ensures this positive definiteness, so the strict positivity of this non-equilibrium steady state. And this is the criterion. So now you look again in this algebraic picture, you look at the operators. There's the effective Hamiltonian, and there are all the jumps, all the L's from the Lindblad generate that. And you put them all in a bag. It's one set. So this L, this index, there are lots of Lindblad jumps normally. And now if you look at the algebraic closure, you're allowed to use all the algebraic operations in your operator algebra. So matrix multiplication, matrix addition, scalar multiplication, and so on. And if under those algebra operations you generate the full operator algebra, then there is guaranteed to be a unique fixed point in the end, which is also strictly positive. Okay, so that's the criterion here. But now the question is, well, it's all nice and well, but this is all very abstract, and how do you check for this? Because you want to really know if the lab gives you some dynamics, you want to check how if this really applies, right? So you look at this operator algebra. I have to zoom in because there will be pictures. And I mean, I will not go through the proofs, but what we actually employ is algebraic graph theory, where now you take those operators in this generator set, but now you interpret them as adjacency matrices of a directed graph. So basically what you do is you choose a basis. So right now it's basis dependent, but we show later that it's actually basis independent. But for the sake of the argument, assume it's basis, you fix some arbitrary basis, and now you represent your operators with respect to the spaces. And now you take those matrices, and now you draw graphs where the vertices, they represent all the basis states, right? All the basis states. And now you construct the graph in accordance with the adjacency matrix given by those operators. So I will visualize it because it's easier to see. Okay, so this is just a lot of nasty mathematics. I will not go over this. This just shows you that you really then are able to generate the full algebra. Basically, you go to the Jordan basis, you apply polynomials on it, because algebra generation, if you have one element, it's just, if you use all algebraic operations, one algebra is just a polynomial or polynomials on this in this element. So you get basically Jordan, canonical Jordan representation, and then you can look at the general structure of a generated algebra element. And what then happens is you now draw those graphs. And so, I mean, there's of course several planar representations, like it's a graph, right? It's abstract. Now you embed it on the plane. And so we do this with concentric circles. So you start with the inner circle, and the number of vertices, they are of course scaling with the number of your degrees of freedom. So if you look at spin lattices, spin chains, and so on, you might have n spin sites, and you have spin on each. So then you have 2 to the n Hilbert space dimension. And so you get, depending on the Hilbert space dimension, you of course get higher and higher numbers of vertices. And so you draw those vertices. And now the rule is, you look at your operators, you represent them with respect to the basis, and you interpret them as adjacency matrix for the directed graph. So this is why we have arrows here, because the direction matters. And you will have a connection from one basis element, from one vertex to the other, whenever there's a non-zero entry in your matrix representation of the operator.
Okay. The graph you're showing us is representing what exactly?
This is now.
It's for.
This is now the. If you look at the jumps.
How can I tell that it's 3 sides looking at the graph?
Because this here now, what we are collecting are 8 vertices. Because you have 2 to the 3, it's 8. Okay. So the Hilbert space. This is why I said the number of vertices scales with the Hilbert space dimension. And so in the beginning, the first picture just showed 2 spins. All right. So here we have just in the innermost concentric ring, we have 4 vertices, 2 to the 2. And now if you go higher and higher, we get 2 to the 3, 2 to the 4. So it always doubles with each spin side, of course. That's just like in spin lattices, you always get a doubling of the Hilbert space dimension. And then what you do is you draw a connection, you draw an arrow, where in your representation matrix, of the operator, the respective entry in the ice row in jth column is non-zero. Doesn't matter what value, it just has to be non-zero. If it's non-zero, then you draw an arrow from the ice vertex to the jth vertex. And now you do this with those matrix elements and you get a graph. And if you follow those instructions, you get a graph that sometimes is connected, sometimes is not connected. And our claim is that you can actually read off almost everything about the dynamics you want from this graph. Like, does it split in several independent subspaces where the evolution is, going on just within the subspace and evolving to a separate fixed point? It decomposes into several sectors of the evolution, or if you only get one. So you see the uniqueness of the fixed point. And the way you do it is that you use lots of nice properties in algebraic graph theory, where you now say, we can show that if this graph has the property of strong connectivity, then it ensures the generation of the full algebra. And strong connectivity is defined as the property that each vertex is connected with each other vertex in both directions. But doesn't have to be direct connection. It could be that this one is connected to this one, and you have intermediary. But there has to be some directed way going from vertex I to vertex j in some way. If that is the case, then I and j, those two vertices, belong mathematically to the same equivalence class. And so what this does, the strong connectivity, it defines an equivalence relation on your vertex set and compartmentalizes, it divides your whole vertex sets into various equivalence classes, which are then called strongly connected components. Because all the vertices that are strongly connected with each other, they are in one strongly connected component. And then the nice thing is, like when you have several strongly connected components, that signals several independent subspaces of evolution. If that is not the case, if there's only one strongly connected component, then it doesn't fall apart, right? They're not several classes. So then you only have one fixed point. You don't have several independent subspaces for the evolution. And you can just see it on the...
Should I interpret this as two components? The one that you're showing us at the moment?
As two components, what do you mean?
I see that the upper half is disconnected from the lower half except for one red connection.
Yeah, exactly. So here we show that. So here you would need this connection to have one strongly connected component. We looked at the Lindblad jumps.
It's only going one way, so it's two connected components. Or two components, isn't it?
Yeah, so exactly. So here you see there as some intrinsic direction, right? It's always going like kind of clockwise, right? And this is crucial. The red one is crucial. You have this if you impose closed boundary conditions, because remember those vertices. They are all basis states, but they are also connected to the lattice sites, right? 2 to the n basis states for n lattice sites. And so it starts and goes around, and then here it would come back to the first lattice site. And if you have open boundary conditions, it's not connected. If you have closed boundary conditions, then this red arrow is present. So this just distinguishes, this is all explained in the paper. I cannot go over the whole thing here, but this just distinguishes open and closed boundary conditions. And so you see on this picture now that the connectivity patterns, they give you the information about the invariant subspaces of evolution and the fixed points. And you can do this now for higher and higher site numbers. And you can...
if you have not an open system, a closed system, would it make any sense to draw a graph like this? Is it possible just with a Hamiltonian and no jump operators?
You could. It's a special case, right? Just as the Schroedinger equation is a special case of the Lindblad equation. You could do it for closed systems, but...
what would you expect to see, in that case?
I mean, closed systems are reversible, right? So there's no, you cannot end up in different end states, right? You can always go back in time, and so you get unitary orbits. So it's very boring. But in open systems, you get all kinds of attractors for abstract dynamical systems, right? There can be limit cycles, there can be very strange attractors like in chaos theory, and so it just actually makes sense for non-reversible dynamics, right? But the point is, we do it for the Lindblad jumps and for the effective Hamiltonian, again for two sides, and then for higher sides, and then you get higher and higher. You look at the connectivity pattern, but then you could say, well, wait a minute, you're always looking at finite numbers, right? Like you're looking at 4 sides now, so you get 2 to the 4 basis elements, and you look at this connectivity pattern, and maybe it's strong, it has strong connectivity, fine for you, but how do you know that this connectivity pattern doesn't break apart or doesn't change with higher lattice side numbers, right? If you go higher and higher up to the thermodynamic limit. Because what really interests us is also in thermodynamic limiting behavior, you know, if you have a unique fixed point or not. And so this was a very crucial thing that we also considered. And so we looked at the thermodynamic limit, and what you actually experience is that those diagrams, those direct graphs that gives you those nice patterns, you know, they are constructed from those adjacency matrices. And if you look at the adjacency matrices, they have the fractal behavior. Because what happens is, like, with addition of more and more sites, what you do in the adjacency matrix is just basically, so for the jump, it's very easy. For the jump, it's just basically taking the diagonal blocks. So for each doubling of the Lindblad space dimension, for each additional lattice side, you put the previous block you had in the diagonal blocks of the new matrix, the new adjacency matrix, and an identity in the lower left. Right? You have always a diagonal here. And you do this over and over. You take this here for some finite size, and then for the next step, from n to n+1, you put those in the diagonal blocks, and you put an identity here. And you do this over and over again. And I mean, we show this here that you really have a nested pattern. You always do the same thing over and over again. But then, of course, you cannot just argue geometrically. I mean, we also show this then here with some mathematics. That this is really the case. You have to use some things of algebraic graph theory, primitivity, irreducibility, and so on. I will not go over this, but I will show you here that what we end up is that we show that you always end up with the same asymptotic limit figure, where you have this fractal pattern. You always concatenate graphs. You have a skeleton, and then of course you have to get over a certain threshold to see the pattern. If you have just two lattice sides, you will not see any nice behavior, right? There are no nice effects. So you need a certain threshold, but once you get over the threshold, you see a connectivity pattern arising, and this doesn't change anymore if you go higher and higher, because you always concatenate the same graph to the previous one. And if you zoom in, you always see so it's kind of a self-similarity. And of course, in the finite picture, you will never see exact self-similarity, but then in thermodynamic limit, it is exact self-similarity. And so this self-similarity in the thermodynamic limit guarantees that those patterns, they don't change, don't break apart. So you don't have to worry about, you know, this whole thing disintegrating then into several connectivity classes, into several components. And so we did the same also here for the effective Hamiltonian. There, I mean, the connectivity pattern looks differently, looks quite different, but you still see, you know, there's a skeleton that forms, and then it, you know, just approaches a certain limit. And so this is what we use to show then that it's actually possible to just use the operators, represent them as graphs, read off the connectivity pattern, and say almost everything you want to know about the dynamics, at least the long-term behavior. So independent subspace evolution, unit fixed point, and so on. But I think I'm quite over time already, so I would like to conclude with those results. And thank you very much for the attention and questions.
So from these pictures, you can tell that this has a unique length.
Yeah. So in this case, we showed that it's strongly connected. Yeah. But then for other systems, it might not. But the nice thing is that our method, our approach works like for arbitrary systems. Right? You give me, or the lab has some evolution in the lab, some open system dynamics. So they give me the generator, and we just look at this effective Hamiltonian and the Lindblad operators. We feed them in our algorithm as input, and then the algorithm spits out you know, if it's strong connectivity or not. And so then it's very easy to identify, okay, we have a unit fixed point. So it depends on the system. And so this will be very useful for people who, you know, study many body systems and they want to know what happens in the thermodynamic limit, and, you know, how are the asymptotic dynamics, and so on. So it's a thing that kind of shows you that sometimes the algebraic structure is very helpful. Like sometimes it might not be the most intuitive one, right? I mean, all this what I showed was very abstract, and sometimes it seemed disconnected to physics, right? Very remote. But the star algebraic picture, and just looking at the operators, the operator algebra, and their patterns and their algebraic structure, sometimes tells you a lot about your system, even though you don't have necessarily the clear physical picture. There's no intuition, at least in the beginning. But it can be very helpful, this perspective. And I tried to justify it in the previous slide. That sometimes just, you know, looking in the Hilbert space setting, and just looking what is evolving there, you know, what is really physically happening.
Can you say exactly what was the system that gave rise to this?
Yes, I can show you. I mean, I had to skip over some stuff, but
because you had this correlation matrix.
yes,
it must have had some specific form.
So this is an example model. So this is a trivial dissipative model. So you have dissipation, and you have n lattice sites, and in general you have these spatial dimensions. And so you have this Hamiltonian, but I think you were asking about the correlation rate. You were asking about this.
This is the one that gives you the information. And
both do, because you need the Hamiltonian for this effective Hamiltonian. So I mean, yeah, I mean this is just part of the proof. But when you start here with the criterion, I mean, there are many things that can be said where you have to be cautious. For instance, there's an intrinsic gauge freedom in the Lindbladian, right? You can shift unitary and non-unitary components around. Like you could put things that are in the dissipative part, and you could redefine your Hamiltonian, and you could put this in the unitary part. And so sometimes when people talk about pure dissipation or unitary dynamics, they have to say this only holds in a specific basis. When the basis is traceless, I mean, this is what Kosakowski did. He chose a basis, and in this basis, you get this Kosakowski matrix C, and then you can really talk about pure dissipation and stuff like this, because then this fixes kind of the unitary and the non-unitary part. So, but in general, you have this gauge freedom, right? So it's always a little bit hard to say what is the jump and what is the Hamiltonian, because you could shift it around. But if you start with this, then the criterion really has this effective Hamiltonian that involves the Hamiltonian and the jumps, and the sum of all the jumps. And then in addition, also the single jumps themselves. Right? And so you have to look at this, and then you construct those digraphs. And what you do is basically, I mean, this is now very short, right? I'm it's very simplified version, but what you do, you're adding up all those adjacency matrices. You have matrices, you just add them all up. Because what you actually care about is non-zero entries. You don't care about the values. Of course, you have to check the proofs that there's no, that there's no interference, right? That you're not like adding things up and get zero and stuff like this because of positive and negative and stuff like this. But this is all taken care of, and then you see that encoding those operators in this algebraic graph theory picture really gives you the structure of the dynamics. And so you wanted to see the model, and so our example model that we use for the pictures is this one here. So here you have this Lindbladian, right? Which is already in its diagonal form, because I think you were asking about the Kosakowski matrix C. Yeah. But here it's already diagonalized. So the lambdas, not the lambdas, the gammas, they are already, that's the spectrum of the Kosakowski matrix. Right?
So yes, if you chose the Gelman basis, you would have always been in the well, anyway, that's okay.
Yeah, I mean, we show that then its basis is independent, but you start with this dissipator, you have a Hamiltonian, you construct the effective Hamiltonian, and then what happens in the proof is you add those matrices up, and then you get a final matrix, and this then determines your directed graph, the connectivity pattern. And then you can look at all the different components of your connectivity of your graph, and then you see those separate components that are independent of each other, and also the implications for the fixed points, for the non-equivalent steady states. That's basically the idea. You do a detour with this representation, but you just use the algebraic structure of the operators without even you're not solving any equations. Like you're not solving the master equation or anything, right? You're not looking really at this. You're just looking at the operator algebra. This was the whole point that I wanted to convey, that there's an algebraic picture that you can use that is sometimes underappreciated, because people always say, well, yeah, but you can always represent this. If you have a C-star algebra, then the GNS construction says I can always find a GNS Hilbert space, right? It's state dependent, but I can always find it, and then I can just look in the Hilbert space picture. Yes, but you could kind of lose the bird's eye perspective, right? You lose this algebraic framework. So this was the point that I was trying to convey.
Is that Nest still in Copenhagen?
Nest?
He's a mathematician.